Hi there, Physics 1 class. Thanks for watching my live stream. Today we're going to be reviewing for test number 3. It is about to go live, I think at 7 o'clock tonight. The test is going to go live, so you can do it. And I hope that you will watch this review. Okay. So what do we need to know for chapter 3? Let's take a look. Okay. So we are dealing with chapter 12 and chapter 13 on this test. The final is going to also cover chapter 9 and the rest of the semester. And I'm going to make all of the tests available once they have been completed. Then that will give you the opportunity to review for what we will be doing. Okay, so let's find the right thing. Here we go. All right. So let's get our page here, and we are going to write down some fundamentally important things that you will need to know for the test. Okay. The first thing we're going to need to know is you are going to need to know about pressure. Alright, so let's start off with, let's say this is test 3 review. Alright. So what are we going to need to know? We're going to need to know about pressure. Okay? So if we have our pressure and we have our initial pressure, so this is a pressure at, say, some depth, then we can describe this pressure as P0, our initial pressure, times rho times GD. And I'm going to try and make this short and sweet because I know that your time is valuable. So we will do our best to make it as short and sweet as possible. Okay, so we have here pressure, and this is, we could also rewrite this as P minus P0 equals rho times GD, and we could say that this is equal to delta P. Okay, so if we know our relative change in pressure, then this will equal rho times G times D. Alright, so this will be, you'll definitely want to know how to use this equation. We also have our equation for pressure. So in general, pressure is equal to the force divided by the area. Okay, so definitely know that. Now, we also have been talking a lot about the buoyant force. Alright, so this has been a pretty important force. And we need to remember that the buoyant force, what is it equal to? Alright, so if you don't remember what the buoyant force is, this would be a really good time to write it on your sheet. And I strongly recommend putting it on your sheet. Okay, so the buoyant force should equal the rho, which is the density of the liquid, times V times G. Alright, so this is the buoyant force, if I am not totally mistaken. Yes, I think that's right. And just one thing, when you're doing these videos live, you can get a little nervous. I sometimes get nervous, but we're gonna we're going to power through it, and we're going to pretend like everything I say is right. So if I make a mistake, then please forgive me. Okay. Yes, that is, I believe that is right. So let's look at an example here. Okay, let's say that we had a person out on the land. Right? So here is our human, and they are on the land. And this is, I'm approximating my human as 2 points. Let's say that they are standing on a scale here on the land. Okay, so they're standing right here. Then let's say their weight is 500 newtons. Right? Then let's say that they get underwater. Right? So now we have a scale underwater, and they do this in hospitals. So we will submerge our human underwater. So we'll put our human underwater here. Right? We don't know what their volume is. Let me see. Okay, so let's say that underwater, when they stand on a similar scale, right, they have their apparent weight is, let's say, 80 newtons. Right, so this is on dry land, this is underwater. So what is the volume that they displace? Right, so that's a good question. How could we find their volume? Well, we know what the density of water is, and so if we know what the buoyant force is, then we could calculate what their volume is. Okay, so we know the buoyant force is their density times volume times gravity. Right, and there's a apparent discrepancy here because when they're underwater, the buoyant force is acting on them. Right, so let's say that gravity is pulling them down, right, times m times g. Now the buoyant force does act on them when they're in air as well, but it's pretty insignificant. Okay, so but underwater, right, we have the force of their mass pulling them down, and we also have the buoyant force pushing them up. Okay, and so this would give us our total normal force here, which is what the scale reads. Right? Now, if they were neutrally buoyant, this would be 0 and they would be floating. You could do this with scuba tanks, but let's consider what our forces are. So they're going to read what's the normal force on the scale. The normal force is going to equal the buoyant force minus their weights. Right? So that's going to be, normal force is going to be N, and we can write it the other way. N is mg minus fb. Alright, so the normal force is going to point up, and this is what's going to be the scale is going to read. Okay, so the force of gravity is pulling them down. It's still bigger than the buoyant force, and so we still get a reading on the scale. Okay, so their weight is going to be bigger. So if we subtract the buoyant force from their weight, that's going to give us the normal force that the scale is going to be pushing back on them. And that's what you're going to read in the scale. Okay? So think about how to do that. Right? And let's take a look at what else we will need to do. All right. Oh, yes. Okay. All right. You will also need to know how to find the kinetic energy of a gas. Right? So if you know the temperature, then you can find the gas. Right? So if a problem asks you to find the kinetic energy, so this would be the average kinetic energy, right? Then we can write the average kinetic energy is equal to 3/2 times kBT. This is Boltzmann's constant, right? And Boltzmann's constant in this case, kB, is going to equal 1.38 times 10 to the minus 23 joules per Kelvin. Okay, so this is the average kinetic energy. Different gas molecules are going to have different amounts of kinetic energy, but that is what we are going to. This will be the average speed. So some will be going much faster, some will be going much slower. This is our average. Okay, so let's say if you have a gas in a closed container, right, and we increase the temperature by some amount, how much will the pressure increase by? Which equation should we use? That depends on the problem, but a good one to remember is PV equals nRT. So if my temperature changes by some amount, then the pressure is going to increase by linearly with temperature. So as temperature goes up, pressure will increase. If temperature goes up by 15%, then the pressure is going to also go up by 15%. Basically, we can say that P is equal to some constant C, if our volume doesn't change, times nRT. We'll just abbreviate that as some constant, T. So I can say, well, if my temperature goes up by 15%, right, so we'll say 115 times T, then my pressure is also going to go up, and so the pressure will increase up to, it'll be 115% of what it was. So if this increases by 15%, the pressure will also increase. Oh, and I'm not showing that on the screen. There, PivNert. Hey, if I always hear students saying PivNert. PV equals nRT. Okay, so all right. So if T goes up by 15%, pressure will also go up by 15%. All right, so PV equals nRT. Let's look at a P versus a PV diagram. Okay, so let's say we have some pressure. Let's look at what we have over here. All right, so this will be pressure times volume for some process. Okay, so if our process starts here and it increases and it looks something about like yay, okay, then we want to know how much work is occurring during this process. Okay, so we hopefully we'll have values here. So the important thing to remember for this problem is you want to be in SI units. Okay, so that means you need to be in pascals and volume needs to be in meters cubed. If you have different units, you need to convert them or you'll get the wrong answer. So always remember SI unit, pascals versus meters cubed, muy importante. Yes, okay. So let's put some numbers in here. Let's say that this is 3 and we're going to be in pascals, okay? And this one is, let's say, 15 pascals, okay? I don't know, I'm just picking random numbers and I always get into trouble when I do that. All right, so we go from, say, 1 meter cubed up here to, let's say, 3 meters cubed. And again, I'm just totally making these numbers up on the fly, so I have no idea if this will, how this will turn out. It'll turn out good, don't worry. Okay, so here we go up to 4 pascals. Okay, so we're in some process here. We'll come over here. Our process goes down this way. We'll come back up over here. We'll have some expansion, and we'll go to a higher volume. Remember that you can only do work if there is a change in volume. So work, let's say, is equal to P times delta V. Right? So if you have a pressure and we have a change in volume, this will give us the work. What does that mean? Well, if we have this graph here, if we could find the area inside of this square, that will tell us the work. So if we can calculate our area in here, we can kind of eyeball it, okay? So we can approximate this as a square, maybe something like yay. and hopefully you can quickly figure out what it is. Okay, let's take a look here. P times delta V. How does this work? Well, remember, pressure is force divided by the area, and we can also write area as delta, so V times the area times D. Oh, and look at this. Our area is not changing, so let's say we have some kind of piston or cylinder. Okay, so let's draw a piston over here. Why not? We're gonna do it. All right. So here's our piston. Okay, we didn't talk about pistons enough, and that's one thing I really regret. We did not discuss pistons enough. Okay, whatever. That's fine. You can read about pistons later. The area here is going to be the surface area of the head of my piston. So if this is changing, that's my area. Well, look right here. The area cancels out. Area is not changing in this, only the distance d. So if d changes here, okay, area is constant. I can bring that on the other side of the delta. So now I'll get F divided by A times A, because that comes over there, times delta D. My areas cancel. So now I have W equals force times the change in distance. And this is just what we saw before. Force times distance, that equals the work. So yes, this is true. Find the area inside of the square, or inside of that diagram. Make sure you convert to the correct units so that doesn't mess you up. Okay, that is very, very important. Okay, let's talk about volume change with temperature. Okay, we didn't get a chance to do an example of this in class. I think you had a homework problem. Okay, but remember, we do have the equation. Let's see. If we have delta V, okay, times the coefficient of volume expansion, okay, and I don't think that's what it's actually called, but it's fine. Like I said, sometimes when I stream, I forget things. It's totally fine. Okay, times VI times delta T. Okay, so always remember, it's okay to make mistakes, and when you're streaming to the entire universe, it's easy to forget things. That's fine. Okay, we're gonna go ahead with this. Okay. Yes, the volume expansion coefficient. I think I messed up my words. That's fine. Okay. So let's imagine we have some liquid here. Okay. There we go. And let's use a piston. We didn't use pistons enough. Why didn't we talk about pistons? Okay. So let's say we have some liquid. We don't know what it is. Right? Could be water. Could be something else. Maybe mercury. Maybe some other liquid metal. It doesn't matter. Okay, maybe milk. Why not milk? Or cooking oil, possibly molasses. How much does molasses change with temperature? I don't know what beta is, so I can't tell you that right now. Okay, so let's say that our liquid, we won't mention what it is. Let's say our liquid changes volume. Okay, so if we have a cylinder here, okay, so let's say we have some kind of cylinder here, right? And we change the temperature of our liquid. Here's our delicious liquid. Let's say it's Diet Dr. Pepper. What could be a more delicious liquid than Dr. Pepper? I can't think of any. Maybe you can. Okay, so if we have Diet Dr. Pepper here, that's really good. I like Diet Dr. Pepper. And we change the temperature, how much will the piston change? That's the question. Okay, so we were given our initial volume. So, oh yes, let's talk about Diet Pepsi. This was a great example, okay? Because I actually had a soda can explode in my car one time. So let's say Diet Pepsi, because this happens with all liquids, okay? The volume change of the Diet Pepsi. Was that enough to explode the can? Well, something did. Maybe it was the liquid, maybe it was the vapor. But let's see what we get. All right, delta T here, that's our change in temperature. not time, it's delta T. We'll write it as a big T. Okay. If we know our initial volume, we'll say this is 12 liquid ounces. And you're going to want to put that in milliliters or cubic centimeters. That's a good one. Then let's say, let's change our volume here. So when we get a change in V, if this is in, say, a piston, okay, the area of the piston is not going to change. So therefore, our change in volume we could write as delta V is equal to A times delta D. Right? So the distance here is changing. This is going to be delta D. There it is. Okay? Delta D is changing. So now we can write A times delta D is equal to beta times VI times delta T. That's my change in temperature. Now I have a formula that will tell me how much this distance is going to change. What's the height difference going to be? So this will be beta times VI times delta T divided by the area. There it is. That's my height that it's going to change. Okay. All right. So what do we have next? Now, these are all relevant things that you will need to know for the test, which is why I'm telling you this. And if I tell you this, believe me, it's true. Okay. So, let's talk about what should we talk about? Oh, yeah, specific heat and latent heat of vaporization. Right? What is a specific heat? Well, this is sort of a measure of how much energy it can hold per the mass. Okay, so now when we turn water into steam, that takes a bunch of energy. Right? So let's say steam was coming in contact with your body. Okay, then my cat wants to come up here with me. All right, Zeus. If you want to help with the review, there's nothing I can do since we're live. Okay, this is my cat. This is my cat, Zeus. Hello, Zeus. How are you today? Okay, so Captain Zeus is with us. I totally forgot what it was. Oh, yes. What is the latent heat of vaporization? Well, this is how much energy it would take to convert something into steam. So if it was to go from steam back into a liquid, this is how much energy it would deposit on your skin. Okay? That number's really big. So let's compare that to, say, if you had liquid water, okay? Then the specific heat for water is much lower. Specific heat for water is 4,186 joules, okay? So that's how much energy it would deposit it per degree Celsius. Okay, so depending on your water, it's how much energy a kilogram of water could hold. Okay, so which would burn you more, steam or water? Something to think about. What do you think, Captain Zeus? Well, Zeus doesn't really like boiling water, so he doesn't want to talk about it right now. Something to think about. Steam or water? Interesting. All right. Let's see. Yes, think about steam and does it burn people? I wonder. All right, hydrostatic weighting. Yes. So know about the specific heat of material, the latent heat of vaporization. Zeus, why are you hiding? Stop that. Okay. Then what is specific gravity? We didn't mention what specific gravity is, but if you want to find the specific gravity of that, you would take the density of whatever material it was you wanted to find the specific gravity of, and you would divide it by some test liquid. Okay? So let's say specific gravity would equal density of your test material divided by the density of your test liquid. Where are you going, Captain Zeus? What are you doing? Okay. Alright. Captain Zeus is with me. Alright. What else do we need to know? Now, speaking of weighing people underwater, what if we went to a different depth and you measured yourself underwater? How would that change? How would that affect your weight? Huh? Something to think about. Yes. Then we should also consider the flow rate. So, what happens when a fluid goes from a larger pipe to a smaller pipe here? Okay. So let's say that I knew what the velocity was over here of my flow, okay, of my liquid, and I wanted to find out what is the velocity of my water going to be over here. Okay? Well, if Q is my flow rate, okay, then so this would be my the amount of cubic meters of liquid per second. That's my flow rate. Okay. And let's see. I think don't worry. These things happen when I'm streaming online. Usually, I edit them out during the videos, but since we're live, I am not gonna do that. There's no editing, is there, Captain Zeus? No, there's not. Maybe later I'll go back and catch it up on YouTube. But since you're watching live, well, it's okay. So, let's see, what do we have? Yes. Peering back in time. We know, or I think we know, okay, that we could write Q, this is my flow rate. Yes. Let's say that V, my flow rate here, equals, this is velocity, is equal to Q, this is my flow rate, so cubic meters per second divided by my area. Okay? So if I know what this is here, I should be able to calculate it over here. More specifically, what are we doing? Zeus, I really don't think that you're helping very much right now, bro. Okay. So, yes, we can write this. We could also write that if my change in volume over here, passing by, has to equal V over here. Those things have to be true. So, I can write A, the cross-sectional area, times the velocity, times my time, and it's not on the screen. There we go. This has to equal the, so this is area 2. We'll call this my cross-sectional area here. This is area 2. There's area 2. And this will be area 1 over here. So this is my cross-sectional area 1 over there. Alright, so this will be equal to A1 times the velocity here times delta t. So what are we saying here? What does this equation mean? Let's talk about it. Well, if I have a big area here, I know that this quantity, A times V, has to equal Q. So over here, Q, my flow rate, will equal A times V. This has to be the same. So if the area gets smaller here, if they might go to a smaller area, the velocity has to increase to accommodate the rate of flow. Okay? So the amount of liquid passing by doesn't change. Okay? This is my cubic meters of liquid per second, that remains constant, right? But in order for that to happen, the velocity has to increase over here to go through these smaller sizes. So the liquid is flowing faster here, and in effect, I also get a drop in pressure. Okay, so for this one, during this time period, we'll get rid of our time here. We'll cancel our times, and so we will have A times V2 is equal to A1 times V1. So if I know my area and my velocity over here, I can solve for my new velocity over here. Okay, so let's take a look. So let's say we know our flow in one area. Okay, so that would be in meters cubed per second. And then we know, let's say, what the diameter is somewhere else. We could find our velocity over there. Okay, so we could solve for our velocity. We could use this equation here, okay, and for a pipe, so Q would equal our area, so this would be pi r squared times V. So if we wanted to solve for our velocity here, then we would have V is equal to Q divided by pi r squared. And I thank you for bearing with me as I stream this to you live. I apologize for any inconsistencies or trouble that I have. It's easy to forget when you're streaming. All right, moving on. That's really the key. You just have to not care about anything, and then you'll be fine. All right, so let me think about what we've done. All right, we did PV diagrams. We did pressure difference. So as we change in depth, so what is the change in pressure? All right, so we did this one here. So as we change in pressure, okay, then how would that be affected by depth? Okay, so this equation is very important. So as we moved deeper into a liquid, how would that change our pressure? Okay. What would happen if we weighed someone underwater at different depths? Would that affect the apparent weight on our scale? How would that affect it? We talked about specific gravity. How could we find the volume of a person if we knew what their change in weight was? So if we put them underwater, we weighed them on dry land, we put them underwater and weighed them. How could we find their volume? Okay, then you need to think about how is energy deposited from steam onto an object. So let's say there's steam flowing by, the steam turns into liquid, and we had, say, a piece of metal. Okay, how much energy would that deposit onto the piece of metal? Okay, what else do we have? We also talked about pistons. So if how would I calculate the change in height here if my volume expanded with temperature? So if I had a temperature change, how could I find the height there? Right? How much would that change? We talked about the change in pressure with change in temperature. Right? We talked about kinetic energy of the molecules. What else do we need to know? You need to know how many moles are in a given volume. So let's say, if I say you have a 1 liter tank of oxygen, how many moles of oxygen would that be? Okay, so review your chemistry. If I say, here's my 1 liter tank of oxygen, how many moles of oxygen would that be? Okay, we talked about moles. What else? Oh yes, here's a good one. So here's what we have so far. Well, we did talk about hot air balloons. Okay. So let's say we have a tank of gas, right? We know the volume of our gas, so let's say we have a scuba tank here. So here is my scuba tank, and let's say that my scuba tank, let's say this has a volume of 3 meters cubed. All right, and it is at a very high pressure. Let's say 8 times 10 to the 6 pascals. Right? If I let this out into the atmosphere, so say here in St. Louis, right? If I let the gas out, right? So here's my tank. I open the thing and it's like, interesting story. Actually, if you take these gas bottles and you put them on a ramp like this, okay, and you take a sledgehammer and you knock off the nozzle, this thing will shoot out like a missile. These construction people were telling me they launched it across the Missouri River. Don't ever do that. It's a very dangerous missile. If these fall over in the lab, these can actually go through a gas wall. So here's something to think about. If we had, this is say 3 meters cubed, the volume in here at a pressure of 8 times 10 to the 6 pascals, and we release all this gas, what will the new volume be? Okay, so what's my volume going to be? Okay. All right, so that pretty much brings us to the end. Let's check to see if there are any comments. Did I allow comments? Well, I don't really know. Looks like there's 4 of you watching. That's going to do it for now. Thank you for watching my live stream. And if you missed it, you'll be able to go back and watch it again later. So with that, I'm going to conclude things, and I will see you later.